Then we will see about the diagonalization of a n cross n matrix. This is the very important topic of a eigenvalues and eigenvectors. We will see the several of its applications, and we can see that how the eigenvalues and eigenvectors are useful in this regard. So diagonalization is actually the important way which gives us the separable entries and gives us a diagonal metric. So first of all, in a diagonalization, when we start about that one, so our objective is to find a metric. If the metric a metric n cross n is available, then is this there exist an invertible matrix P such that P inverse A and P is diagonal? So this is the very important question. And diagonal means a metric which has only the diagonal entries. The upper entries are zero and the lower entries are also the zero. Only the diagonal entries of a matrix exist. And moreover, for a metric n cross n, does a metric A have n linearly independent eigenvectors? So for on getting the answer of these two problems, we have the following results in this regard. So first of all, we will see the definition. There is a one definition that if A and B are two square matrices mean the metric have same number of rows and same number of columns. Then we say that the metric B is similar to A if there exists an invertible metric P such that the metric B is equal to P inverse A and P. So if for a metric A and B, if we get a metric P which is invertible means a metric P, the inverse of metric P exists, and if we multiply P inverse on the left side and P on the right side, and it will be equal to the B of A. So, moreover, this is the important definition of his two similar metrics, and important to see that if A is every metric A is similar to itself. Like you can add the identity metric on the first side and identity metric on the other side, because the inverse of identity metric is a identity metric. And secondly, if A is in similar to the B and then B is also similar to the A. And the final thing is that if a metric A is invertible to B and B is invertible to the C, metric C, then the metric A is also invertible to the metric C. So these are the some of related things about the similar metrics. But when we comes up to the diagonalization, so it have some useful things. But first of all, we will start from here that in a similar matrix there are some useful things about that. So the important question, how this metric P we can find it. So we can find a metric P which satisfies this relation. So for this, remember that the determinant of A and P inverse P is always the same. Like this is a good relation that P inverse A and P, if you take determinant of this metric, because the products of a matrix are always the same metric when they are square metric. And also if A is invertible, then P inverse AP is also invertible. Both have the same or inverse of the both matrix exist. And moreover, if the rank of A and P inverse P is also the same, like mean both have the same number of non-zero rows. Similarly, A and P inverse AP have the same nullity. Both have the same trace, both have the same characteristic polynomial, and both have the same eigenvalues. And the dimension of eigenspace of the both have also the same. So these are some important characteristics in this regard. Now, let us see that if a metric A is said to be diagonal, the metric A is said to be diagonalizable if a similar metric P to some diagonal metric, that is, if there exists a diagonal metric P such that P inverse AP is diagonal. So this is the definition of a diagonalization metric, that if a metric is diagonalizable if there exists a metric P which is invertible and such that P inverse AP is a diagonal metric. Diagonal metric means a metric is said to be the D which has only the diagonal entries. So in this way, we said the metric P is said to be diagonalized A, like the metric P exists which is diagonalizable. So now the important thing how this metric P we can obtain. The method is very similar, very easy to get a metric P. And so first of all, we will go through few results and then we will see that how such a metric P exists. There is a one important result in this regard that the following two statements are equivalent for a n cross n metric. A metric A is diagonalizable if the metric A has linearly independent eigenvectors. So linearly independent means all the eigenvectors are independent from each other. So this makes a one good relation. Look, if a metric A is diagonalizable, then it means there exists a metric D, diagonal metric, such that P inverse AP is equal to the D, where P is any invertible metric. And so the D we can find easily and P we can find easily, and we can also say about a metric that it's diagonalizable or not. So here we have some criteria regarding that. So how to find this diagonalizable metric? So the method is the same as we know how to find the eigenvalues and eigenvectors. As in the previous lesson, we saw that for every square metric, we can find its eigenvalues and eigenvectors. When we can find its eigenvalues and eigenvectors, then with the help of all of its eigenvectors, like the first vector is p, second vector is first vector is p1, the second eigenvector is p2, and suppose the last vector is pn. So just write them into the column form and make a metric p. So if the all eigenvalues are distinct, then these P1, P2 up to Pn will also be the distinct, and with its combination, we can generate a metric P. And remember that if the all eigenvectors are independent, then P inverse always exists. And such if the P inverse exists, then we can combine it like P inverse AP, that is always equal to the metric D. And the metric D contains the eigenvalues into its diagonal entries. So one can always be verify that P inverse AP is equal to a metric D, which have only the diagonal entries like D1, D2 up to Dn. For example, this is the good example and simple example that how to find a metric P that diagonalizes a given metric A. So suppose we have this metric A. So we need to find its eigenvalues and eigenvectors. We know that if a metric A is available, then we can find its eigenvector by using the relation that uh, like a uh, ax equal to lambda x. So a the lambda I minus a is equal to just take determinant of lambda I minus a equal to the 0, then we can get the characteristic polynomial, and this characteristic polynomial always gives us the eigenvalues. So 1 is the eigenvalue and 2 is also the eigenvalue. Here 2 is the repeated eigenvalue. So repeated mean the multiplicity of this polynomial is 2. It means the eigenvalue is 1, 2 and 2. So remember that if the P has a multiplicity 2, it means it will gives you the two eigenvectors or two eigenspaces. So first is like P1 and P2 is here. These are the eigenvectors of a lambda is equal to 2. And for second eigenvalue, lambda equal to 1, the eigenvector is minus 2 and 1. Now, if we combine, like, if we take the first of eigenvector P1 here, P2 here, and P3 here, with taking of any relation, then this will gives us a metric P. So look,
Sorry,
all
sir.
these three are
We
independent.
can't see the screen anymore.
Hello, can you hear me?
Yes, we can hear you, but we can't see the screen, the
Uh,
demonstrations.
so other guys, can you also not see the screen because the screen is already shared from my side?
No, sir, we can't
No,
see
we
your
can't see.
Okay, wait a second. Can you see the screen now?
Yes, we can. Thank you, sir.
Okay, thank you. So, if there is something, so please tell me in advance so that I can correct it immediately. Okay, thank you. So here, as we remember that we say about the similar metric. So similar metrics are those metric where a metric A is similar to B if there exists an invertible metric P such that B is equal to P inverse and P. So where P is any metric which is invertible. So important thing is how to find a metric P. So for that, for this definition of a similar metric, we have another important definition of a diagonalizable metric. So we say that a square metric is diagonalizable if we can find a metric P such that P inverse A P is equal to the diagonal metric D. So here the diagonal metric we can easily find. So the method is very simple. Since we know that if we have a metric A, then we can find its eigenvalues and eigenvectors. With the combination of these eigenvectors, we can arrange it and then we can find a metric P. So when we get a metric P, so we can see that P inverse A, P is always equal to a metric D, which is a diagonal metric, and that diagonal entries are always lambda 1, lambda 2 up to lambda n. For instance, if we have a given metric A, so we need to check that is this metric diagonalizable or not. If it's diagonalizable, how to diagonalize it and how to find a metric P which is invertible and P inverse A and P is equal to the D, and it will solve many things for us. For example, for a metric, we can find its eigenvalues and eigenvectors, as we saw in the last topic that from this we can make a characteristic equation and solve it by determinant of lambda I minus a is equal to 0. Then we can get its roots. So for instance, here the eigenvalues are 1, 2, and 2. 2 and 2 mean here the multiplicity of 2 is 2. It means the eigenvalue 2 is repeated. And one can check that the sum of eigenvalues is always equal to the sum of diagonal entries of a matrix. So the sum of 0 plus 2 plus 3 means sum of these diagonal entries is what is 5. And here you can check the sum of eigenvalues. So the eigenvalues are 2, 2 and 1. So 2 is repeated because the multiplicity of this 2, lambda minus 2 is 2. So it means 2 plus 2 is 4 and 4 plus 1 is 5. Here you can check that the eigenvalues are the eigenvalues are correct or not. Now, when you find the eigenvalues, then the next task is need to find the eigenspace or eigenvectors. So for lambda is equal to 2, we have the two eigenvectors p1 and p2. Remember that when we find this, they are always independent to each other. And for lambda is equal to 1, the eigenvector is minus 2, 1 and 1. Now if we combine these three vectors, like just put p1 here, p2 here and p3 here, then with its combination, we get a metric P. And remember that all these three vectors are independent to each other because these have no relations. These are coming from eigenspace. And this metric P is always invertible, mean its inverse always exists. So when its inverse exists, so we can find its inverse and we can check that P inverse A and P. So this is P inverse, this is the given metric A, and this is the P. If you multiply them, then you will get a diagonal metric. So the diagonal metric always obtain the diagonal entries. So the diagonal entries are eigenvectors like 2, 2, and 1. And check that you can see that 2, 2, and 1 are the eigen values. So it means that the diagonal matrix always contains the diagonal entries. One thing here you can remember that if you can interchange the P1, P2 and P3 here. For example, if you write P3 1 here and here you can put P2 and here P3. Then if you multiply them, then here it will comes the 1. The lambda is equal to 1 here, then 2 and 2 because it's depend upon the order of a eigenvectors. If you interchange the order, then still P is invertible. And it means P will not always be unique. P can be any form of its columns. But if you interchange them, then the eigenvalues will also interchange here. So this will gives us important relation. Here it means this is the P, and one can check that P inverse A and P gives us equal to the D, which where D is a diagonal metric. So there are some examples of a metric which are not diagonalizable. For example, there is a for instance, if you have a metric P, then you need to find its eigenvalues and eigenvectors. When you find its eigenvalues and eigenvectors, then look for 2, you can get only the one eigenvector, and here for P you can also get only the one eigenvector. And it from P1 and P2, although these two are independent, but there will be no third row when you for which you can combine it and write in the way like this: P1, P2, P3. So if this doesn't make this kind of a metric which is independent, then such a metric will never be diagonalizable, because there are not three P1, P2, P3s from which you can get a metric P. So this is the examples for that, and also it means that there will be another row which is zero, and hence this metric is not diagonalizable. Now this diagonalizable gives us some useful relations. For instance, if v1, v2, v up to vk are eigenvectors of a metric A corresponding to the distinct eigenvalues, then these all v1, v2 up to vn are linearly independent. Mean distinct eigenvectors gives us an independent, linearly independent independent vectors. So these are independent vectors when all the eigenvalues are independent. And here there is a one useful result, like if A is n cross n metric that have a distinct eigenvalues. Like all eigenvalues are different. Suppose there are three eigenvalues, 1, 2, 3, all are different, then this metric A must be diagonalizable. Why? Because if they have independent eigenvalues, then they must have independent eigenvectors. And with these independent eigenvectors, you can generate a metric P with P1, P2, and P3. For example, here this is a good example of this theorem. Like if we have a metric A, if you find its eigenvalues, like eigenvalues, just take a determinant of a lambda I minus a is equal to 0, then you will get these three roots. Like lambda 1 is 4, lambda 2 is 2 plus uh, under root 3, and lambda 3 is 2 minus under root 3. So it means these are the three distinct eigenvalues. Now, when these are three distinct eigenvalues with then it means this metric is always diagonalizable, and the if we can easily find a metric P which is invertible. And here for that metric P, if you write P, if you find P inverse and multiply P inverse with A and P, then its combination will gives us a diagonal metric D, where D is a diagonal metric obtaining only its diagonal entries, which are 4, 2 plus under root 3, and 2 minus under root 3. And remember, the metric D is we can simply find, and also the metric P is P is with the help of eigen vectors, and the metric D is coming with the eigenvalues on the diagonal places or diagonal entries. So these are the results about that one. And here you can see that if we have a upper triangular or low triangular metric, then we can simply find its eigenvalues. Like the eigenvalues are minus 1, 3, 5, and minus 2. So remember that all the eigenvalues are distinct. If the eigenvalues are distinct, then these metric will must be diagonalizable. So it means we can get the distinct eigenvectors, and with the combination of that in the form of a row, we can get a metric P which is diagonalizable. So it will also gives us a one very useful result. For example, we know that if a metric A is diagonalizable, then we can find a metric P such that P inverse A and P is equal to the D, where D matrix always obtained the eigenvalues on its diagonal entries places here of that one. Now, if we take it square, when we take it square, it will become 0, and we know that the square of a diagonal metric is only the square of its diagonal entries. So it is d square. Now, if you multiply P inverse A and P, it means just multiply again with that. So when we multiply, then P, the square of this one is right two times P inverse P, then P inverse P. And we know that P in and P inverse will be cancelled and it gives us identity metric over here. And A times A, it will becomes A square. Now it means the P inverse A and P whole square is just simply P inverse A square and P. And then similarly, if we take any of its power, if we take its power k, then P inverse A power k, P is equal to D power k. And this gives us a one simple idea that you can move the P inverse on the other side when apply the P inverse on the right hand side, then P will be cancelled from the right side and it goes to the side of a D. And also P inverse, we can remove it and it comes to the other side and its P comes on the left of with the D. So it means A power K is equal to P D K P inverse is equal to this. So d power k is coming over here and we can simply get this relation. And this relation is very important and this will gives us that we can find a power k or a square a cube without making any of its square with the help of this relation. Now, this relation, we can find it, and here there is a one useful example. For example, find the a power 13, where a is this metric. So there is a long method, like we can do a square, a cube, and multiply again and again. But with the help of this formula, we can simply find its. And there is also one exercise, one assignment problem for you to find the a power n with any power with any value of that one. So here you can see that if the metric a, if a is invertible, then we can find a metric, find its eigenvalues and eigenvector. So the eigenvectors are here p1, p2, p3. So with the combination of that, we can find a p, and also we can find p inverse by the relation by finding P inverse. When P is available, we can find P inverse. And the metric D contains always its diagonal entries, which are 2, 2, and 1. So the, we know that D is equal to this one. And then we can also write the A is equal to P, D, and P inverse. And when we apply its A power 13, then it means it will becomes P D13 P inverse. D13 means just take the 13 of the diagonal entries. So if we take the A power, the diagonal entries power 13 and multiply with the P and then P inverse on that. Either you first multiply these and then the resultant multiply with the other one, or first you multiply the second and third and then their answer metric multiply with the first one. Then you will get this kind of a metric, and this metric will always be a power 13. So this is the simplest rule for obtaining of that one, which you need to be get in this way. So here we in the last lesson we saw that if lambda is the eigenvalue of a, then lambda square is the eigenvalue of a square, and also this kind of results we have saw before. And one more thing is that the converse of theorem number 5.2.3 is false. It means that look, if the eigenvalues are distinct, then metric A is diagonalizable. And if metric A is diagonalizable, then it doesn't mean that the eigenvalues are also distinct. Because in the first example, we saw that eigenvalues are 1, 2, 2, but still the metric A is diagonalizable. So it is based on not on the eigenvalues, but it's based on the eigenvectors. So all the eigenvectors must be distinct. Because if the eigenvectors are distinct, then we can find its diagonalization. Here there are some examples for that. You can see that find a metric P that diagonalizes a metric, a 2 cross 2 metric. Now we can go through with that one, and we can see that how this metric is diagonalizable. You know that we just for first we need to find its eigenvalues. The eigenvalues are determinant of a minus lambda I is equal to 0, or you can also compute determinant of lambda I minus a is equal to 0. With the help of that, we get characteristic polynomial equations, which is here you can see that this difference gives you the 2 cross 2 metric, and when to take its determinant, like first entry multiply with fourth entry minus second entry multiply with the third entry, so it will give us a polynomial, which is we also call a characteristic polynomial. Then find its root. When we find its root, it will give us the two roots. One is 8 and minus 1. So one can check that either these values are correct or not. So just make it sum. 8 plus minus 7, which gives us 7. 8 plus minus 1 is equal to 7. So the sum of eigenvalue is 7. Now you can check that what is the sum of diagonal entries, which is also called trace. 5 plus 2 is also 7. So it means eigenvalues are correct, because 5 plus 2 is 7, and here 8 plus minus 1 is also equal to the 7. Now, when the eigenvalues are correct, the next task is to find the corresponding eigen vectors. So first eigenvector corresponding to lambda is equal to lambda 1, which is 8. So put the value 8 in the place of lambda over here and solve it. Now, if we put lambda is equal to 8 and solve the characteristic polynomial ax equal to lambda x, then it will give us the eigen vector corresponding to that one. So here the complete solution of that, this will gives you the simple homogeneous system, and you know the how to find the solution of a homogeneous system. We know that the solution of homogeneous system is always a eigenspace, which is called the null space. So this will gives us a null space. So it means it will gives us an eigenvector. So the corresponding eigenvector is minus 1 and 1. For it means lambda 1 is equal to 8, and its eigenvector is p1, which is minus 1 and 1. Now secondly, the need to find the eigenvector corresponding to lambda 2, which is minus 1. So put lambda minus 1 in the place of lambda in the above equation, where ax equal to lambda x. So when you find its solution, it again gives you the homogeneous system, and for that homogeneous system need to find its solution space. So when we solve it by any method, we will get its solution, and from this solution we will get a vector, which is the basis of that one and also called the eigenvector. So the 1 by 2 comma 1 is the eigenvector corresponding to lambda 2, which is minus 1. Now when we have the first p1 is actually the minus 1 and 1, and p2 is the 1 by 2 and 1. Now you combine it, just make a metric P, which is P1 and P2. P1 means first column, P2 means second column. And then in this way you get a metric P. So remember that this metric is always invertible. Why? Because both eigen values are independent, so both eigenvectors are also independent. So if this is so, then with the combination of that, we can make a metric D, which is diagonal metric. So in the diagonal metric, you just put the diagonal entries lambda 1, the first eigenvalue, in the place of a first one, which is the 8. And the second eigenvalue is 2, just put 2 over here. So it will gives you 8008. So this is the D. Now you can verify that if you find P inverse, A is available over here and P is also here, that is always equal to the D. D mean diagonal entries. Again, I tell you that if you interchange P2 right first, P1 right second, then this D will also interchange its eigenvalues. So then the minus 1 will come in the first place of a eigen value, and the second eigenvalue will be interchanged. This eigenvalue will also becoming interchange. Now here you can verify that if you find the P inverse, then multiply first A and P, then AP is coming over here. Then if you multiply P inverse with AP, then the answer will be equal to 800 minus 1. And 800 minus 1 is what? The diagonal metric, which obtaining always the diagonal entries. So in this way, you need to solve this problem. Here there is another example for you. Like if A is a metric, need to find its diagonal entries. First of all, need to find its eigenvalues. The eigenvalues are 0, 3, 3, and you can verify that if these are the eigenvalues, then the sum of eigenvalues is always equal to the sum of diagonal entries, like 0 plus 4 plus 2, which is 6, and then 0 plus 3 plus 3, which is also 6. Now need to find its eigenvectors. For lambda is equal to 0, the eigenvector is 3 minus 1 and 1. And for lambda is equal to 3, there are two eigenvectors which are p2 and p3, mean minus 1, 0, 1, and also minus 1, 1, and 0. If these are the values, then with the combination of p1, p2, p3, you can make a metric p, and this metric is always diagonalizable. Means this metric p is always invertible because all the values these are distinct. These three vectors are independent to each other. With its combination, we make a metric P, and the here the D will be just write the diagonal metric 0, 3, 3, where 0 is the first eigenvalue, 3 is the second eigenvalue, and again the 3 is the third eigenvalue. If you find P inverse, then this is the P inverse, and one can check that P inverse P is equal to a metric D, which is a diagonal metric. So this is the method to obtain the diagonalization of any given metric A. It means this metric A is diagonalizable, and we have a metric P which is invertible, and P inverse AP is equal to the D. So this is the topic, and if you will see some of its problem, like here, there is a one simple solution of this problem number 24, that find a power n for if n is any positive integer and a is the metric. So you need to find its eigenvalues and eigenvectors with the this is also the simple way. So when the eigenvalues are available, then with the help of eigenvalues, we can find its eigenvectors, and then from that eigenvectors, we can find a we have a relation, this relation. Here I can tell you that this relation is available over here, that a power k or a power n is equal to a power k is equal to p d power k and p inverse. Now just put the values over here, and in this way we can find a power k. So this is the method for finding these values. Now if you have any question, you can ask your question. Here the method is also available over here, so of that one. So you need to be go through from that one. For example, if you like here I can show you one example of that one. For instance, like we know that a metric A is diagonalizable, and like for instance, here we can see that since the example I can show you that here there is a result. If A is any square metric which is diagonalizable, then A power k is equal to p times d and then p inverse. So this is basically relation which we can use it to find the any power of that one. So here this relation is also available in the textbook, like a power k is equal to this. Now remember that we have already seen this example, like here uh, example, here we have a metric A which is given as A is a 2 cross 2 metric we have, and suppose the entries of a metric A is are 5 minus 3 minus 6 and 2. Yes, this is the metric A, and we know that how to find its eigenvalues and eigenvectors. And since like for this value we know we already computed a metric P, which is the metric P has a this is the metric P which is minus 1 1 is, then here we have the 1 by 2, and the next is 1. So this is the metric P. We all also, if the metric P is available, then we also can find its inverse. The inverse need to be found in the same way as we saw in the elementary linear algebra. So the P inverse in this case, we know that it's just like 2 by 3, and then minus 1. Here the entries are again, say the 1 by 2, and here is 1 and 1. So this is uh, the P inverse. D is also available. D always contained the diagonal entries, which are the eigenvalues. So in this case, we saw that the D is only the 8, 0, 0, and minus 1. So if this is the D, now someone asks you that we know this relation, so we can find its values. Like for instance, what about the A square? Then the A square means see this relation, which is equal to the P d power to, here it's the d power k. Remember that the d power k will becomes, it's comes with the power of that one, and here we just put the d square, and then again the P inverse, and we know that the value of P is available over here, so just put the metric P multiply with the metric D, which contains the diagonal entries over here in the place of D square. D square, we know that how to find it, just take the square on its diagonal entries. So here just you make the square of that one, and then furthermore the P inverse is it comes like here in this way. Now we know that the constant we can take the common from the outside, like this was the common entry, so just write the 2 by 3 over here first, and then we need to write the second entry over here, this one, and then here we know that the square of 8 is the 64, and the square of minus 1 is 1, and this will remain same because the common we took in the outside. Now this is very simple to just multiply here, like this is the solution form of that one is, and look here, the thing will become simple. For instance, if you just multiply them, if you multiply them, then we can simply get the square metric. Either we can multiply the, here we can just take the 2 by 3 common, maybe, like it's no problem, and then here either you first multiply these two and then their answer will be multiplied with the third one, or you can multiply the second and third metric first and then it's multiply with the first metric. Then with this relation we can get a square. So this is the method to find a power square. Similarly, if you need to find a power n, then it is just simply to take the p, then d power n, and then p inverse, because it doesn't affect on that power, and like it's just will be writing the things in this way. So just you need to be take the power n, whatever the values of n, and then when you take its multiplication, so this multiplication will gives you the value of that. So just make the n as a fixed number and just need to multiply these entries with the product of that entries. We will get like here you just can take this constant from remove over here, and then rest of that just need to multiply, and with its multiplication we can simply get a metric which is the a power n. Here we can just this is just like a product of that, and I hope you know that how to multiply that metric. So with the help of this multiplication we can get the answer. So this is the method to obtain the entry the a power n, and this diagonalization is very important. From this diagonalization we can also find the inverse of that one, and also here a power n. So there are the many applications of diagonalization of a metric, and also the eigenvalues and eigenvectors. So here we saw this application that this diagonalization is important to find the a power n, whatever the value of n is. Now, if you have any question, you can ask your question, please. So the summary of the topic is that if you have any metric A, which is square metric, then you need to find its eigenvalues and then corresponding eigenvectors. So with the help of eigenvalues, you can find its eigenvector. With the eigenvectors, you can make a metric P. If all the eigenvectors are distinct, then it means metric is diagonalizable. And with the combination of that, it will gives you metric P. And from that metric P, we can find its P inverse. Then when we multiply the metric P inverse A and P, then it will gives you a metric D. That D metric is always a diagonal metric, and that diagonal its diagonal entries are the given eigen values, which are like here you can see the eigen values are available over here. So these are the eigenvalues coming from that. And one thing more is if you find a power 2, a power 3, so you can use this relation that there is a useful formula for that. Means if a is any metric, then this is the result that if a is any square metric which is diagonalizable, then you can write a power k is equal to p inverse dk and P inverse. So for here we saw that example that if A is a metric, then we have a P and P inverse. D is also available. For making D square, just A square, just put the D square entries and multiply all of that. We will get the square of metric. Similarly, for A power n, just we can compute it and we can get the values. And similarly one can make a inverse. If like if a is invertible, just put a power the a its inverse mean a power minus 1. Then here the inverse entries will come over here as well, and then with the help of that what we can do is we can just multiply and we can get a inverse. But that is giving us a very special case in case of a metric which is invertible. But a power n, just making doing of that, and after multiplication one can get these entries. So this is the method, and if you have any question then you can ask your question, please. Okay, I will upload the notes of these diagonalizations, and also the lecture will be uploaded in the my Moodle website. So you can go through. If you have any question, then you can ask your question. Okay, if there is no question, then best wishes for you and goodbye.